Welcome to the Getting Started with Geostudio video series. This tutorial guides new users through the basics of defining a stability analysis in SLOPE3D. In this video, we will cover how to set up the analysis settings for SLOPE3D, defining and applying material properties, how to set up the slip surface search using EntryExit or the cuckoo method, how to define the pore water pressures using a piezometric surface. In SLOPE3D, spherical and ellipsoidal slip surfaces are generated using the equation for a hybrid ellipsoid. X', Y', and Z' are the local axes. We use local axes because the slip surface could be oriented in any random direction in 3D space. The principal semi-axes are A, B, and C. N is an exponent that can be used to flatten the tips of the hybrid ellipsoid in the Z' direction. The principal axis, C, which is aligned with the Z' axis, that is, the axes orthogonal to the X', Y' vertical plane, is determined from the aspect ratio K. Let's consider some examples. Starting with A equal to B, and the aspect ratio set to 1, we get the following perfect sphere if n equals 2. If the principal axes stay the same and the exponent n is increased to 4, we get flatter ends on the ellipsoid. If n is changed to 1, we get this shape. Setting n back to 2, which is equivalent to a sphere, and then changing the aspect ratio from 1 to 1.5 means that the ellipsoid is elongated in the Z' direction. Finally, setting the aspect ratio to 0.6 with an exponent n of 2 has the opposite effect. In order to define an entry-exit search, the first step is to create an entry grid and an exit grid. At solve time, a point on one grid is connected to a point on the other grid to form the primary principal axes of the ellipsoid. In 2D, we can easily visualize these points being connected and then geometry being used to generate the arc of a circle. Effectively, the same is true in 3D, except that the parameters of the ellipsoid equation are used to generate the final shape. Let's now review the workflow for setting up a 3D stability analysis in Geostudio. In the Geostudio project, notice that the 3D geometry has already been added. As discussed in a previous video, the geometry for a 3D stability analysis can be defined either using parametric geometry, or in this case, an import of a geological model directly from Central. This model was created in Leapfrog, and so the model volumes that come in are shown in the Geometry Explorer in this section right here. For simplicity, this model only has a single geological unit, and for that reason, we only see one geological model volume imported. Now that this is done, I can click on Define Project and add a 3D limit equilibrium analysis to the tree. Just like in 2D, the first step is to rename the analysis. Then we select the analysis type. In SLOPE3D, we have Morgenstern Price, Spencer, Bishop, and Yanbu. With Morgenstern Price selected, I then choose either a half sign, constant, or other inter-column force function. The default is half sign. Next, we define the pore water pressures. Because the geometry is defined using a geological model volume, the pore pressure conditions cannot be defined using a finite element analysis in SLOPE3D. As such, we can choose one of our other options, including a piezometric surface. On the Slip Surface tab, our first selection is either ellipsoid or sphere. As I noted in the PowerPoint, the ellipsoid shape defaults to sphere when the exponent n is set to 2. Underneath this, we have two search options. The first one is entry and exit. The second one is a nature-inspired optimization algorithm called Cuckoo. On the Convergence tab, we have a number of settings just like we do in 2D. First off, we can set the minimum slip surface depth. Secondly, the minimum slip surface volume. Underneath that, we have our convergence settings, including the maximum number of iterations, the tolerable difference in the factor of safety, and then the option to perform under relaxation. Finally, we have our solution settings, which in this case is defaulted to the root finder. These default settings are identical to the settings for a 2D analysis. Once the analysis definition is done, I can now close this dialog box. Now I can click on the Draw, Slip Surface, Entry Exit, and the dialog box opens up. We can draw these entry and exit grids in three-dimensional space by clicking on the domain. In this case, it might be more ideal to look from the top down, and so I'll select the top of the cube, which rotates the view, and then I'll zoom in to the area of interest. I can click on the Entry Grid tab, and then anywhere on the domain, I'll begin the clicking process. If I click 2 times and right-click, I can exit, and now the entry zone is defined by a single line. Similarly, I could click once and then right-click, and now the entry would be defined by a single point. For demonstration purposes, I'm going to redraw the grid by clicking once, then twice, and then a third time. With the grid drawn, the next step is to define the number of increments. Again, this is very similar to 2D. Between vertex 1 and vertex 2, I will have 4 increments, which means 5 points. And similarly, between 2 and 3, I'll enter 4, giving us a 5 by 5 grid of points in the entry zone. The next entry is the radius increments. For this example, I'll put 4. In the lower portion of the dialog box, we have our aspect ratio and our n exponent. At current, the aspect ratio, k, is set to 1, which means the radius of the ellipsoid in the z prime direction will be equal to the radius in the x prime and the vertical y prime directions. We can also add additional ratios. So for example, I'll put an aspect ratio of 0.8 and 1.2 in the list. Similarly, we could alter the n exponent. Then I'll click on the exit grid and repeat the process. Notice that the radius increments are automatically set because there is only one definition for the radius increments. If I change it in this dialog box, it'll change in the other dialog box. Clicking on the Exit Grid tab, I can now click once, twice, and 3 times, and then enter in the increments. Once that's complete, I can close this dialog box. Rotating back into more of a 3D view, we now see the entry and exit grids draped over the ground surface. The next thing I'm going to do is to define the piezometric surface. In a 2-dimensional analysis, we can go and draw a piezometric surface manually, or we can import a set of points to define a polyline. In 3D, you'll notice that the Draw Piezometric Surface menu is absent. That's because piezometric surfaces are defined using background meshes. Now, in some simple cases, we could, for example, choose a construction plane, like the XY plane on the back right here, and then sketch in 2D, zoom in, and I could draw a polyline at some elevation, again, just for demonstration purposes. Let's say like that. Then right-click to exit, hit OK. Now with that complete, you'll notice that we have this polyline showing up as a profile in the Geometry Explorer. But at this point, we do not have any geometry items outside of our geological model volumes in the file. I'm going to right-click and extrude this polyline 500 meters. And we'll notice that when I do that, the plane only covers a small portion of the domain. So I'll double click in here and I'll try 2000 meters. And now the plane covers the entire model domain. With that done, I'm going to hit OK. And when complete, we'll notice both the profile and the extrude operation are now in the design history. Also, under the geometry dropdown, we now have a surface. With this surface in place, I'm going to right-click and convert to background mesh. That same menu operation is found up in the toolbar right here, where we convert to background mesh and then choose a body, a plane, or a face, like so. I'll then hit OK, and under the background meshes, we see that now a background mesh exists, and it's called Mesh 27. During the conversion process, I could have renamed it to Piezometric Surface. Now when I go up to Define, Pour Water Pressure, and Add, we see our background mesh in the list. And so I can hit OK, and now it is part of the analysis. Notice, however, that the material list is not populated. Now for demonstration purposes, I want to show you the second way to bring in a background mesh external to the file. So to do that, I'm going to delete this, close this, delete the background mesh, and I'll hide the surface. Before bringing in the background mesh, I'm going to define materials. Now defining materials is identical to slope W. We define materials, add a new material, rename it. In this case, I'll just rename it granite. Select a material model, change the color if desired, and then enter the correct parameters. Nearly all the material models available in a 2D analysis are available in 3D. With that done, I will select the geological model volume to which I want to apply the material, and down in the property sheet, I will select under the associations dropdown the correct material for this volume. Okay, with that material applied, now I'm going to show the second way of bringing in a background mesh. I'll click on Import. Notice that we have a section called Background Mesh. If I have a certain file of STL, OBJ, DWG, or DXF format, I could bring it in directly through this menu. In this case, I'm going to import a background mesh from Sequence Central. This will connect me to all the projects in which a Leapfrog model has been created and published to a central server. Here I'll select the Geotech server. Then I'll find the project. We see a list of meshes that have been published. And in this case, I'm just going to bring in the topography mesh. Now, unlike the geological model volume, which is fully three-dimensional meshed volume, in this case, we're bringing in a 2D mesh representing the topography. I'll hit OK, and you'll notice it loading down in the bottom right. Once it's done loading, the first thing we notice is that it's oriented in the wrong position in three-dimensional space. That's because Leapfrog has the axis Z in the up direction, whereas Geostudio uses the Y Cartesian axis for up. Over in the property sheet, we can remap the axes and adjust the base point. For this example, because I've already brought in the geological model volume, I'm going to select a transformation that I already saved for this file. When I do that, notice that the topographic mesh overlays with the geological model. For simplicity, I want to assume that the water table mimics the topography of this hill slope. And based on some measurements, let's assume that the water table was around 50 meters vertically downwards, measured, say, at this road. So I'm going to go back to the background mesh, edit, and I'm going to adjust the Y coordinate right here to go downwards by 50 meters or thereabouts. So I'll just enter a value of 9. And if I rotate this way, you can see that the topographic mesh shifted downwards. Now in a real problem, I may have a mesh, a 2D mesh that actually represents the piezometric surface. And so then it would be located properly in space. But again, just for demonstration purposes, we're going to use the topography. With that done, I'll hit OK. It asks me if I want to change the updated transformation template, to which I will say no. And now with that done, we have our background mesh imported. Currently, it's very difficult to see, and so I'm going to select my geological model volume and change the opacity to 0.2. Now we can see the position of our background mesh relative to the domain. With that done, I will go to Define, Pore Water Pressure, Add One, choose the topography, and hit OK. In the Materials tab, we see that the piezometric surface is applied to our granite material. With the entry-exit defined, materials and pore water pressures defined, we're now ready to solve the analysis. Before leaving this video, the last thing I want to point out is the cuckoo method. Now, unlike entry-exit, the cuckoo method does not require any intervention to define a search zone. And so I can go to Define Project, right-click, add an analysis, and clone this first analysis. I'll rename it. Then on the Slip Surface tab, we'll select the search technique. Close this dialog box. I'm going to click on the volume and change the opacity back to 1. And now, as noted, we do not need to define the search zone. And so if I was to solve this analysis, the cuckoo technique would search the entire geometry to find the most critical slip surface. However, if I did want to constrain it into a certain area, I would click on Draw, Slip Surface Limits, and again, in either 3D view or in a plan view, we can use the entire ground surface extents or specify points on the ground surface. In this case, I'm simply going to draw a zone that focuses the cuckoo search in this area here. And so we begin to click. And once we're done, we right-click to close the area. Now both these analyses are ready to be solved. Thanks for watching.